Hey math kids, we have one more example in this section, and it says to use the Mclaren series that's on the screen to find the Maclaurin series for this. Okay, so to do that, we just need to plug in negative x squared and negative 1/2 to this formula. So 1 minus x squared to the negative 1/2 is going to give us this. Actually, let's save ourselves some writing. If we plug in 0 to this, we're going to get 1 to the negative 1/2, which is just 1. So our first term is 1, and then we can change this to k equals 1 and go from there. And p comes from here, so that's negative 1/2. And if we do negative 1/2 minus 3/2, or minus 1, we get negative 3/2. If we think of this like a negative 2/2 to do that. Dot, dot, dot. If we do, we're plugging in, let's see, we can do p, which is 1/2, negative 1/2, and that positive 1 would combine to make a positive 1/2 minus k. Then we get x squared raised to the k, and all of this is over k factorial. Okay, from here, we'll kind of simplify this to x to the 2k. And, oh, whoops, this is supposed to be negative x right there. And then we can take out a negative 1 to the k. So all of this became this. Okay, we still have our negative 1/2, our negative 3/2, dot, dot, dot. And then we want to kind of write this in a form that's all over 2. So we do 2/2 right here. We can get negative 2k plus 1/2. And this is still over k factorial. Still have the summation and all of that. Okay. The next thing we're going to do, we're going to make this a little bit simpler. We can pull out a 2 times 2 times 2 times 2 times 2, lots of 2's. And so these 2's will just become a 2 to the k on the bottom. And then we can do a negative 1 times negative 1 times negative 1 times negative 1, which is going to come out as another negative 1 to the k. So these negatives now go away, and those would kind of swap like that. Now I'll rewrite what we have with a few simplifications. So we're going to do 1 times 3 times dot, dot, dot times 2k minus 1. The bottom is 2 to the k, k factorial. Then we still have this, x to the 2k. Now, these negative 1's can combine to be negative 1 to the 2k, but if this is always an even number, negative 1 is going to become a 1, and so if we multiply this by 1, it doesn't change anything, and so that's where that's going. Okay, this is looking a little bit better. Now, this part is a bit of a stretch to come up with on your own, but just bear with me. So what I'm going to do, I want to try to turn this into like a factorial of some sort. So notice how we're missing the even numbers. So I'm going to do 2 times 4 times 6 and go all the way up to 2k. And then I'll do that on the bottom as well because I don't want to change the value. So that's really just like multiplying by a special 1. Now, if we do that, we're going to have 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 dot 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 all the way up to 2k. So if we combine this and this, it's actually just 2k factorial. So I'm going to change that, 2k factorial. Okay. We still have x to the 2k. And on the bottom, what we're going to do here is we're going to factor out a 2. And that would give us 1 times 2 times 3 times 4 all the way up to k. And so that's really just going to be 2 times 2 times 2 times 2 times 2. It's not really factoring out, sorry. It's like 2 times 2 times 2 times 2 times 2. So it's a 2 to the k. And then this is left to be a k factorial. And then we already have that same thing there. So it's like we have 2 of those on the bottom now. Okay, we still have our summation. K equals 1 plus right there. Okay, and then the last step, we're just going to combine these. So that would be 2 to the 2k, which becomes 4 to the k. And then we would have 2k factorials would be k factorial squared. And so our final answer for this part is going to be 1 plus summation from k equals 1 to infinity. We have 2k quantity factorial over 4 to the k factorial quantity squared. And then we have x to the 2k. All right. Now, our original bound is this, and so for this one, x squared is bound, must be less than 1, and that's within this range as well, and so we're good. Okay, we're going to keep moving on. So this is part B. It says arc cosine of x minus arc cosine of 0 is equal to 0x negative 1 over square root of 1 minus t squared dt. And they want us to find the Maclaurin series for arc cosine and which x values it's valid. Okay. So the thing that we looked at last time was 1 minus x squared to the negative 1/2, which is really just 1 over 1 minus x squared under a square root. So it may have not been obvious, but this is like the same thing, this entire thing right here, except for it's not negative. So first thing we're going to do is find the arc cosine of 0. Arc cosine of 0 is pi halves. I'm going to pull this negative out in front, so we're just left with what we found on part A, and so I'll just write that here. Okay. Now, if we take the antiderivative, all of this is just going to be a constant, so we don't have to worry too much about that. we're just going to carry that down. It's a constant attached to a variable, but a coefficient, I guess I should say. Okay, now we're going to do our antiderivative with this, where we get t to the 2k plus 1, and then we divide by that, 2k plus 1, and then, okay, so that's that, and then the 1 is just going to become a t. And then all of this is evaluated from x to 0 to x. We have the negative sign that's still out there. And this is still equal to arc cosine x minus pi halves. Okay. If we evaluate this at x, we're just going to rewrite all of these values. All these t's are just going to become x's. And if we evaluate it at 0, that will go to 0. This will go to 0, and 0 times anything is 0. So it'll just be 0, so we can kind of throw out that idea. So just in the interest of saving some writing, I'm just going to get rid of these t's and change them to x's. And distribute the negative as well, so that's negative, and this is negative, so that's gone, this is gone, and then I'm going to add the pi halves over here to create my final answer. So arc cosine x, I add pi halves and add pi halves, is going to equal pi halves minus x minus this, okay, and then remember originally it was valid for absolute value of x is less than 1. And so the domain of arc cosine, all of this is going to be valid from -1 to 1. Okay? Now, let's see. We're going to look at, trying to see if I can get away with erasing this or not. Part C says, hence find the first 3 non-zero terms of arc cosine x squared. So we can see the first 2 terms pretty easily right there. And then we want to evaluate this by plugging in the first k value. So if we plug that in, we're going to get a 1, a 1, and a 1. And so if we do that, we're going to get 4 times 1 times 3. So the bottom of that is going to be 12. And if we plug in a 1 right here, we get 2 factorial, so that's a 2. So that simplifies to 1/6. And then we're going to get x raised to the 2 times 1 is 2, plus 1 is 3. So we get that, and then it was negative. So that's our third term. So let me erase this. Okay, so arc cosine of x is approximately pi halves minus x minus 1/6 x cubed. And let me just erase the rest of this. Okay. Now, if we find arc cosine of x squared, like they ask us, we're just going to plug in x squared for all of those. Once again, it's good for those x values. Okay. Now, they asked us in this problem to find from 0 to 0.4 arc cosine of x squared dx. And so if we're using this approximation, it's going to look like this. We take the antiderivative of this, we get pi halves x minus x cubed over 3 minus x to the 7 to the 7 over 7, and then we still have the 6 multiplied right there. Okay. Now, if we do 6 times 7, we get 42. And then we just need to plug, if we plug in a 0, it all goes away. So we really just need to plug in the 0.4. And that's going to be our answer. Add another parenthesis just to be safe. And subtract that, we get 0.4. Raised to the 7. Add another parenthesis. Divided by 42. Okay, and we get 0.607. Okay, if you have additional questions, please come to Math Lab. Until then, calculator.